Hi everybody, this is Jim Corkins with the second part of 5.0 rotational motion, and this is going to be mostly focused on problem solving. So again, if you haven't done the reading, please do so. Here are the OpenStax chapters for Physics 101 and 111, and Survey chapters as well. For Physics 121, here are the OpenStax chapters and the night chapters. And for everyone, 101, 111, 121, the collected chapters are 9 and 10. Okay? So we're going to be focused on the problem-solving portion. But first, before we do that, let's talk about how, remember when we were doing Introduction to Motion back in 1.0, how we had motion diagrams? Well, there's motion diagrams for angular things as well. So looking at this wheel right here, they've got it labeled where you could see omega, which is the angular velocity, and it seems like this wheel is going to be rotating counterclockwise, okay? And 0 seconds will indicate time 0. 1, 2, 3, 4, 5, 6. So basically they're showing this wheel rotating from 0 to 1 seconds. And now it'll be here. 1 to 2 seconds, 2 to 3 seconds, 3 to 4 seconds, 5, 6 seconds, right? So if you notice, the two dots are close together, and then they're getting further apart, a little bit further apart, a little bit further apart, a little bit further apart, and a little bit further apart. So if the dots go close together, and then they go to separating, well, that's indicative of speeding up motion. So speeding up in the counterclockwise direction. All right. So translational motion wise, the dots, these two dots, this distance together, I'm going to try to draw this. So if this were the center of the wheel, 0 seconds would be right here. 0 seconds would be right here. And then I'm going to try to get this distance matched right there. And that's 1 second. And again, the circumference of the circle is the distance it's moving in the x direction as it rolls. So this distance from 1 to 2 seconds is literally this distance from here to here. We just have to measure this, you know, with a tape measure or something like that. And then 3 seconds. And 4 seconds seems to be just a squidge longer. And then 5 seconds seems just to be a squidge longer. And then 6 seconds looks like it's right there. So this distance right here from 5 to 6 is this distance right here. Okay, so you can see from 0 to 1 seconds, it goes from here to here, and that matches up with this distance right here. So this is exactly the same motion diagrams that we've been using since chapter 1 for motion. Whoops, that arrow is right there. This arrow is right here. And the 4 to 5, this distance right here is this distance right to there. And 5 to 6, finally. All right. Oops. So further, we can see that this wheel, it looks like it only spun a half turn, so 180 degrees. So this distance right here in the x direction is basically only a half revolution, right? So the distance it turned right here would be the number of revolutions. In this case, it would be delta theta would be ReV theta for 1 revolution, and it looks like it did 1/2 revolution. And it did that in a period of time of 6 seconds. Well, the distance it rolled through would be, again, the number of revolutions the angular displacement in revolutions times 2 pi r. Okay? And let's say this wheel is, I don't know, a third of a meter, actually a half meter. Let's say the radius of this is a half meter. So r equals 1/2 meter. Well, then that means this distance would be a half revolution. Actually, let's do a third meter. Let's say the radius is a third meter. Well, then this is going to be, the distance it rolls is going to be a half revolution times 2 times pi times 2 pi times a radius of 1/3 a meter. So overall, this distance, 1/2 times 2 and 1/3 times 3, let me see, what is pi divided by 3 equals 1.05 meters. So this displacement in the x direction from this point, let's say it's at 0 meters and it rolled to the left, is going to be 1.05 meters. Okay? To the left. So that would be negative 1.05 meters if it started out at the center of the wheel is at 0 meters in 0 seconds. So it'd be negative 1.05 meters is that distance, or that displacement rather. And so now we could get a lot of interesting information with that. Just a little bit of information like how far it rotated, and the radius of the wheel, and the time. We could get a lot of information. Well, now, if we said it started out at with an initial velocity, initial rotation of 0 revolutions per second, well, now we know that it's sped up to a half revolution in 6 seconds. So omega final would be a half revolution divided by 6 seconds. So that'd be, it's rotating at basically 1/12 a revolution per second, or 1 revolution every 12 seconds. You can see it that way. And we could get the acceleration too. Since omega final is equal to omega initial plus alpha times t, well, then we can see that the acceleration is omega final divided by t, which is going to be 1/12 a revolution per second divided by 6 seconds, which is going to work out to be 1 over, what is that, 72 revolutions per second squared. So we could get a whole bunch of information from this. We could also get how far it went in the, what was its final velocity, what is linear final velocity? Well, that would be 1/12. It'd be omega revolutions times 2 pi r. And we could actually get its linear acceleration from that too, which is going to be the angular acceleration times 2 pi r. So we're gonna work through this and do a bunch of very specific problems where we can get a whole bunch of information just with a little bit, with a short amount of with very little information given. Okay. Before we do that, let's talk about plotting graphs. Okay. Because omega and alpha are going to be in the z direction, and that means counterclockwise is the positive revolution. And this should be displacement, not distance. Displacement. displacement. This is linear displacement versus time. This is revolution versus time, angular velocity versus time, linear velocity versus time. So since angular stuff seems to be in positive and negative z, and displacement in this case is going to be in the x direction, so this is going to be delta x, and this is going to be v sub x. Those problems are kind of, those two directions can seem to be in opposing directions. So for example, if you notice the z direction here, this angular velocity is rotating in the positive z direction, or it's got a positive angular rotation. However, when we plotted the wheel as it's rolling counterclockwise, it's rolling in the negative direction, or it's got a negative displacement. So that's kind of strange, and it would be the same thing for the y direction if it was moving up and down. So they might seem to be opposites of each other. So my point is, you can't always say that if it's got a positive revolutions, it's going to have a positive displacement, linear displacement. So just be careful of that. Okay, so let's go with a similar type of problem, except this one is going to be rotating. It's going to be rotating counterclockwise, but it's going to have a 7th second. So it starts at the 0 second mark, rotates all the way through counterclockwise to the 7th second. And it looks like, just like our last problem, it looks like since the dots are close together and they're getting further and further apart, that it's speeding up. Which means, if it's speeding up in the counterclockwise, we'll say it starts at 0 revolutions. It's going to be speeding up much like this, right? It's going to be speeding up, so it's going to be not only rotating in the positive direction, but it's going to have a positive angular acceleration too, because speed up means angular acceleration, angular velocity, they're in the same direction. Well, we've seen this graph before in motion, and that works out, since we're only dealing with constant accelerations, that's going to look like this. It starts out at a low velocity and speeds up to some high velocity. Incidentally, it looks like it's going to be rotating through 0.75 revolutions as it's speeding up. And this distance is going to be, by the way, that's 3/4 a revolution. This angular velocity looks like it's going to get to 3/4 a revolution in 7 seconds. So that's 3/4 a revolution divided by 7 seconds, which is going to be 3/28, and 3 divided by 28 is 0.1. So I'll just leave it in fractions. So this is 7 seconds. So this is 3/28 revolutions per second. Okay. Well, displacement in the x direction we saw from the last one, it's actually going to be rotating in the negative direction. That means it's going to be the wheel itself, the center of the wheel, is going to have a negative velocity vector in the x direction. Now, you don't know where it started at, so let's say it started out here. It had a positive initial displacement, or actually, to be consistent with the last problem, we said it actually started out at the 0 meter mark, which means if it's moving in the negative direction, it's going to be speeding up in the negative direction. Okay. And again, if this wheel is a half meter, then it's going to be rotating 3/4 a revolution times 2 pi times a half meter. Actually, I said a third meter. Okay. So that means the distance or displacement it's going to get to in the x direction is going to be 3 divided by 3, so that's 2 divided by that, so it's 1/2, so it's going to be 3.14 divided by 2. So it's going to be just over, so this is basically going to be pi divided by 2. So 1.57. So this is going to be 1.57 meters. In the negative direction. So that's going to be its displacement. So it's going to get to here, which is going to be negative 1.57 meters. Well, if it's speeding up in the negative direction at a constant acceleration, then it's going to be working just like this. And the velocity in the x direction is going to be the number of rotations, so it's going to be omega rev times 2 pi r, right? So in the x direction, this is going to be 3/28 revolutions per second times 2 pi times 1/3 of a meter. So this is going to be, what's 2 divided by 28? So this is going to be pi over 16. So what's pi over 16 equal to? So pi divided by 16. That's 0.1. So that's 0.20 meters per second. So this is going to speed up to a negative 0.20 meters per second. So that's going to occur right here, negative 0.20 meters per second, if it started from rest, right? If it started from rest, it started out with the velocity of 0, and then it gets to this speed in 7 seconds, okay? And so this rotational speed in 7 seconds, multiply that by the circumference of the circle, and you see how far it's actually gone. Okay, so there will be graphing that's involved with this. Incidentally, the slope of this line is the acceleration. So we could get that from the time, the delta x, and the final velocity and the initial velocity pretty easily. It would just be this velocity divided by time. So the acceleration in the linear acceleration in the x direction would be negative 0.20 meters per second divided by 7 seconds. And the angular acceleration here is just going to be the linear velocity divided by time. So it'd be 3/28 revolutions per second divided by 7 seconds. So 3/28 times 7. And that would be revolutions per second squared. Okay? So graphing is still going to be important. There's some other graphs if you want to try them out. You want to try graphing a wheel rotating, speeding up in the same direction that we did before. A is basically this first one that we just did. So maybe try B, slowing down as it starts here, rotating clockwise to the over 6 seconds. This wheel, C, is rotating counterclockwise and slowing down over 6 seconds. D is going to be speeding up, rotating clockwise over 6 seconds. So you could try graphing these and doing those on your own or in class. But it's actually better if we try it with a lot more detail than what we've been doing. So let's try a slow down one. We've done 2 speeding up ones. Let's try a slow down one, and let's try this one right here. This looks like a good one. So there's a few pieces of information. So this wheel looks like it starts out at 0 seconds, and the next second is 1 second over here. So it looks like it's rotating clockwise, and the dots are getting closer and closer together until it ends at the 7-second mark. So this looks like a wheel slowing down as it's rotating clockwise over the period of 7 seconds. And it looks like it rotates through 3/4 of a revolution. Okay? So what I want you to do is pause the video and try filling out all these blanks. Start with the angular stuff first, and then move on to the linear stuff. And you might have to use some of these equations of motion to do it. So pause the video and try it on your own right now. All right, so hopefully you had a chance to try this out. Well, let's go ahead and start with the angular information first. So again, it starts at the 0 seconds, rotates through all the way through 7 seconds, and ends right here. It looks like it leaves a gap of about 90 degrees, or about pi/2 radians. Or just, if you want to think, the gap is about a 1/4 revolution. So this basically goes through 3/4 of a revolution. Okay? And let's say it ends, it says right here in the problem, it ends at 0 revolutions per second. Okay, and so they want the angular velocity. So we have delta theta, we have omega final, and we have time, which is 7 seconds. We do not have acceleration at this point. So look for the one equation that doesn't have acceleration, and that can help us figure out what the initial omega is. In this case, omega sub 0. All right, well, it's this one. So let's do some math. So delta theta is going to be equal to omega final plus omega initial divided by 2 times t. All right. Now we need to find out what omega initial is. Omega final is 0. So I'm going to just do a real quick. So this is going to be omega initial divided by 2 times t. Well, in order to isolate omega initial, we're going to multiply both sides by 2 delta theta, and divide both sides by t. And this is our initial omega. So our initial omega here is going to be 2 times the number of revolutions over the period of time. Well, the number of revolutions is going to be 3/4. So this is 2 times 3/4 a revolution divided by 7 seconds. So this is going to be 3 divided by 4. 2 divided by 4 is going to be 3/2. And that is going to be, so this is going to turn out to be 3/14 a revolution per second. So 3/14 of revolution per second. That is what delta theta is. I mean, that's what initial angular velocity is. Well, cool. That makes things a lot easier. Let's get the angular acceleration. Let's use the simplest equation that we could use. Now that we have time, delta theta, omega initial, omega final, let's use the most simple equation to get what angular acceleration is. Well, right here looks like it. In fact, this initial velocity right there is going to be 0. So omega final is going to be equal to alpha times t, which means omega initial, I should say. Boy, that was wrong. Let's rewind that for a second. We're trying to find omega final is 0. So this is 0. Well, omega final equals omega initial plus alpha times t. Okay. Oops. I'll talk about, after I fill the numbers out here, I'm going to talk about the directions in a second. So here we go. So this is going to be equal to 0. I'm going to subtract omega initial to both sides. omega initial is going to be equal to alpha times t. And so omega initial divided by t is going to be equal to alpha. Well, omega initial is going to be 3 over 14, 3/14, and the amount of time is 7, so 7 times 14 is going to be equal to 98. So this is going to be 3 over 98 revolutions per second squared. 3 over 98 revolutions per second squared. Well, now that we're here, and we've got our amplitudes for each one, or magnitudes for each one of these done, let's figure out the directions. Well, this thing is rotating clockwise, which means its displacement is going to be negative. Remember, clockwise is negative. And that means its initial angular velocity is going to be negative as well. But it's slowing down, okay? Which means its angular velocity, which is negative, is going to be countered by its angular acceleration. So this is going to be a positive number right there. All right, cool. Well, let's go ahead and do the linear velocity. So the center of the wheel is going to be rotating. So the center of the wheel is going to be moving to the right, but it's going to be slowing down. That means it's going to be accelerating to the left. So this acceleration vector is going to be negative. The linear velocity vector is going to be positive, and the displacement is going to be positive. Okay? Well, since we have the angular stuff finished pretty easily, to get the linear stuff from that, all we do is just take the angular component and multiply it by the circumference of the circle. The radius is 2 meters. So this is going to be 3/4 a revolution times 2 pi times 2 meters. Okay? So this is going to be 3/4. 2 times 2 is going to be 4. Divided by 4 is 1. So 3 times pi. So what is that? 3 times, where's the little pi icon? Right there. Equals 9.42. So this is going to be 9.42 meters as the wheel moves to the right. To get the linear initial velocity, we're going to take the magnitude of the angular velocity, I should say. So 3/14 revolutions per second, and we're going to multiply that by 2 pi times 2 meters. Okay, so that's going to be 2 divided by 14 is going to be 1/7. So this is going to be 3 times pi times 2. So 3 times pi is 9.42 times 2 equals, divided by 7 equals 2.7. So 2.70 meters per second. Well, the angular acceleration portion linear acceleration portion is no different than the angular stuff for no different from the linear velocity and linear displacement. We're going to take the angular acceleration, 3 over 98 revolutions per second squared, and we're going to multiply that by 2 by the circumference of the circle. So this is just going to be a big mess. So basically, I'm going to 3 times 2 times pi times 2 equals, divided by 98 equals. 0.6 meters per second. So this is going to be negative 0.60 meters per second squared. Okay, so this is a way to break down basically what we've been doing before on these other videos with the for earlier part of this video with graphs and this part here. It's a little bit more organized, okay, and you will have to use the your equations down here, your equations of motion, to fill in some of the blanks. But as you can see, once you've got the angular parts finished, then you could just fill out the linear parts really easily. If it's in revolutions, you just multiply it by the circumference of the circle. If this were radians, you would just have to multiply it by r, because 3/4 of revolution, you multiply that by 2 pi, and that's now a radian. So there's a lot of ways you could do this, but keeping it in revolutions, just like I said in the first video, and then multiply it by the circumference of the circle is pretty easy to do. Okay, so in your free time, I want you to go through these other two problems, have it speeding up as the wheel rotates clockwise, and it's a half-meter wheel. Try it out, and then check with your instructor. Well, now we're at where we're actually doing problems that you would get from your book, okay? So I'm going to start up a whiteboard, and I'm going to screen grab this guy right here. I'm going to snip it. And this is a problem that I think I took from the book, or one of the books maybe, not sure. Thank you, Microsoft, I got it. Well, let's go ahead and try this out. So I'm going to increase this so we could actually read it pretty well. All right, here we go. There's a crankshaft of a race car that goes from 90 revolutions to rest over the period of 3 seconds. Okay, and they want to know first, what is the angular acceleration? They want to know how many revolutions does it make it through, and then finally, if they give you the diameter of the wheel, how far did the car move? I'm actually going to make this a little bit larger. Okay, well, just like I taught you in the very beginning, I want you to list out all of the variables, okay? Delta theta, and luckily this is all in revolutions. Omega initial, omega final, angular acceleration, and time. Okay? Let's not worry about the linear velocity stuff just yet. All right. So let's see what we have here. You have a crankshaft that starts out at 90 revolutions per second and goes to rest. So that's going to be 0 revolutions per second over the period of 3 seconds. And they're initially asking for what is the angular acceleration. So right now we don't have delta theta. Okay, so we're given an initial omega, a final omega, and time, and we want the angular acceleration. Well, let's look at this equation, and we're going to look for, actually counterintuitive, you want to look for the one variable that you're going to want to use one equation that is where the variable that we don't have is not given. So delta theta we don't have, and we're not trying to find for delta theta, we're trying to find for angular acceleration. Well, anything with theta in it, we can't use. So basically these bottom 3 equations right here, we can't use. We need to use omega final equals omega initial plus alpha times t. And actually I'll use delta t to be consistent. Okay, so this object is going to be slowing down. All right, so let's have it rotating initially in the positive direction, positive omega direction. And that means we're going to probably find out that our omega is going to be, our alpha is going to be 0. So if we draw a picture, this is going to be a wheel that is rotating with a positive omega, and it's going to be accelerating in the negative acceleration direction. That means this wheel should be moving to the left with a negative velocity in the x direction, but it should have a positive acceleration, linear acceleration. Okay? So that'll come into play in this very last part, I think. The linear velocity and linear acceleration. Anyways, starting out, omega final is going to be 0. And now we have 0 is equal to omega initial plus alpha times delta t. Subtract omega to both sides. So in this case, we're just going to put in the magnitudes of stuff since we're going to be finding for our directions in here as well. So this is alpha times delta t. Divide both sides by delta t. And that is what alpha is. So in this case, this is going to be negative 90 revolutions per second over a period of 3 seconds. So it looks like alpha is going to be, what is that? Negative 30. Negative 30 revolutions per second squared. So this is going to be negative 30 revolutions per second squared. 30. Very cool. Okay. Well, now that we have the acceleration, so I'm now going to put in negative 30 revolutions per second squared here. Well, now in the next question, we're trying to find delta theta, or the angular displacement. Well, we know that is going to be, that should be a positive number, because the omega is positive. That means it's spinning counterclockwise, is what we chose. It doesn't say in the problem, but if you don't know what the direction is in the problem, they don't give it to you. Actually, they do, positive 90. So, okay, cool. Well, here we go. Delta theta is going to be, we could use any of these equations right here. Any of this. The easiest one, it looks like, is this bottom one right here. Okay. And so let's go ahead and try it out. Delta theta is going to be equal to 1/2 omega final plus omega initial times delta t. Well, omega final is 0. Omega initial times delta t. So delta theta here is going to be equal to omega initial over 2 times delta t. And that is going to be equal to 90 revolutions per second divided by 2 times 3 seconds. Let me rewrite that 3 so it's more legible. So delta theta looks like it's going to be, I'm going to pull out my calculator, 90, so that's 180. 90 times 3 is 180. 180 divided by 2. 2 equals, you know what, I'm just going to start over. 90 times 3 divided by 2 equals, alright, so 90 times 3 is not 180. that's 270 divided by 2. So that's 135. So it looks like it makes 135 revolutions in the period of 3 seconds. Okay? All right. Well, now that we have everything in terms of revolutions, to get how far the car moved, just like in the last problem that we just did, to get what delta x is, which is what they're asking for, this guy is going to be rotating counterclockwise. That means it's going to have a displacement which is going to be negative, but this is going to be 135 revolutions, right? It's going to be delta theta. Actually, I'll just start out with that. So this is going to be delta theta times 2 pi r. So this is going to work out to be negative 135 revolutions times 2 times pi times 0.45 meters. Well, let's see what that's equal to. I'm going to just trust my calculator right now and not think. 135 times 2 times pi times 0.45. So just check my math up here. So this is going to work out to be 381.7 meters in the negative direction. .70 meters in the negative direction. Meters. So this is the typical type of problem that you'll run into when you're doing homework problems in this chapter. Okay. Usually they just keep it with angular things, like it's a drill bit rotating or something like that. But in the case if it's a wheel or like a yo-yo or something like that, it may have some linear motion. So it's best to just solve things angularly. And then if you need to go to the linear part, you just multiply your revolution stuff by 2 pi r. Again, if this is in revolutions, or the velocities, since you have omega, you just multiply that by 2 pi r if you have omega in revolutions. And if they want the linear accelerations, you just take the alpha in revolutions and multiply it by 2 pi r. Do all your heavy lifting using your rotational motion equations and then convert them over later on to this, to the linear motion stuff. Okay? So it's a little bit easier to do if you do it in that process. So that's why I had you practice here with the angular stuff first before you moved on to the linear stuff. And at that point, you were just multiplying it by 2 pi r. Okay? So this one is typical of the type of problems that you will be doing in most of your homework problems, right? You have a speed drill that's rotating counterclockwise, and it's going to take 2.5 seconds to speed up to 2,400 revolutions per second. They want to know what the drill's angular acceleration. So we're going to start this problem just like we've done every other problem. Make a list of the variables that you have. So we're going to make a list of all the variables. Alpha and delta t. Okay. So they want to know what the angular acceleration is in the very first part. The drill looks like it's rotating counterclockwise in 2.5 seconds. To speed up, I'm assuming that means from rest. This is in the night textbook. Okay. And, whoops, 2,400 revolutions per second. Revolutions per second. So we don't know what delta x is. So we're doing a very similar problem to what we just did. Okay, we got to get omega initial is 0. So we're going to use this top equation because it doesn't have any delta thetas in it. We're not given delta theta. So omega final equals omega initial plus alpha t. And since it's going to be rotating, it's rotating counterclockwise and it's speeding up. So its alpha is positive and its omega is positive. So all these are positive. The initial omega is 0. So this means omega final divided by delta t is going to be alpha. So this is going to be 2,400 revolutions per second divided by time, which is going to be 2.5 seconds. So alpha should be equal to 2,400 divided by 2.5 equals 960. So this should be 960 revolutions per second squared. Well, once we have that, to find the part B, to find out what delta theta is, we're going to just use our simplest equations that we could use right here. Well, maybe in this case we could use this one right here. That's actually maybe simple. Omega delta t plus 1/2 alpha t delta t squared. Omega initial is 0. So delta theta is going to just be equal to 1/2 alpha delta t squared, which is going to be equal to 1/2 times 960 revolutions per second squared times 2.5 seconds that we're going to square. All right. So 2.5 squared times 960, 6,000, divided by 2, 3,000. So this is going to go through 3,000 revolutions. Wow. This is going to spin 3,000 times over 2.5 seconds. That's amazing. These are the typical kind of problems that you're going to have to do for this chapter. Okay. Now, Knight does a similar type of problems, except this problem is it starts out and it does have an initial rotational velocity, angular velocity. It's then going to speed up to a higher angular velocity over the period of 3 seconds. So you're going to be doing basically the same thing that we just did. We're going to be using omega final equals omega initial plus alpha times t. And they want to know just how many revolutions does a crankshaft get through. Well, to do this, well, we have omega initial, we have omega final, okay, over the period of 3 seconds. We don't have angular acceleration, and they want delta theta, right? So we're going to make a quick list of what we have. Don't have delta theta. We have omega initial, which is going to be, we're going to just keep it in revolutions. Well, we got to probably convert revolutions per minute. 500 revolutions per minute. And that's going to be 500 times, what is that, 60? So that's actually going to be 500 to, let me see, That's going to be 500 revolutions per minute divided by 60 seconds per minute, which is going to be 50 divided by 6. So that's going to work out to be 50 divided by 6 equals 8.33 repeating revolutions per second. So convert everything to the base units in seconds. If they give it to you in minutes, omega final, they give it to you at 2,500 revolutions per minute, and that's just going to be 2,500 divided by 60. So that's going to be 41.67 revolutions per second. Let's go ahead and erase this. I think they did want us to find the number of revolutions. Alpha we don't have, and delta t we do have, which is 3 seconds, right? So we're trying to find delta theta. We don't have alpha, so can't use the top equation. Second equation here we can't use. Can't use the third equation. Basically we have to use this equation right here, right? So he's basically going to march us through that. Okay. And he's going to convert to radians per second. I'd prefer you just keep it in revolutions per second, because the revolution is going to end up working itself out. And it looks like he actually finds the angular acceleration first, and then finds the angular displacement. But using what we were using over here, delta theta is going to be equal to 41.67 is our final revolutions per second, plus 8.33 revolutions per second is our initial, divided by 2 times 3 seconds. Okay, so the way we're doing it, I think, is a little bit easier, because we're not stopping off and finding out what the angular acceleration is. Divided by 2 equals times 3 equals 74.99. So basically 75. So this looks like it's going through 75 revolutions over that 3 seconds. Okay. Let's just check real quick. There we go. Yeah, and he got 75 as well. So I think the way we're doing it is pretty simple. It gets to the point. You list out the variables that you have. List out all the variables that you have and don't have. List out the one that you're solving for with the question mark. Cross out the variable that you don't have. That tells you which equation not to use. Anything with alpha in it, don't use it. We use this one to find it, and got it really simply in basically one shot. Much quicker than Knight did. Well, that's basically the end of this video. So please go through the tutorials and check with your instructors as you're going through those tutorials, and work with your groups. The tutorials encourage you to list out the variables that you have and don't have. So please use that. Okay? Have a good night.